Okay, now we're going to see another exercise, number 32, on the same section, section 4.2. This is on page 198. The exercise is asking to prove in full detail that the set of vectors x, 2x, with the standard operations with vectors in R2 is a vector space. So let me write that down here for you. Okay, here it is. Um, Now notice that this is, okay, what is in W? What kinds of vectors are in there? Well, those are vectors in R2, right? It has two coordinates, as you can see here, where the second coordinate is twice the first coordinate, okay? So those are the kind of vectors that are in W. But we need to show that W is a vector space. So we need to go through all those axioms, all those properties, and show that each one holds. Okay, so let's start with the first one. The first one is the closure. Okay, closure of multiplication, of addition. So if I pick two vectors in there, and then if I add them, the addition needs to be in W. Okay. Notice that I cannot pick a particular vector. So I cannot pick, for example, 2 and 4. I know that this vector is in there, right? The second coordinate is twice the first. And then pick another one, let's say 5 and 10. And then we add, this would give us what? 7, 14. Yeah, it's in there. But that doesn't show property number 1 because I pick only two particular vectors. I need to pick two general vectors, okay? So it's not enough to pick only a particular vector. So we need to pick two general vectors. So let's pick 2 in W. Pick 2. So let's put here in parentheses, general vectors. Because you want to show that it works for any vector in there, any two vectors in there, okay? In W. So let me cross this out, because that shows only for a particular example. So here they are. I pick x1, 2x1. That's one vector in there. Here's another general vector, x2, 2x2. Okay? So here they are. Now let's add them. So it's very easy. As you can see, one of my kids is crying there. So it's probably fighting for a video game or something. Here, let's add the second vector. Okay, so it's the standard operation, okay, for vector. So it's x1. Did I put x1 here? There it is. x1 plus x2, and then 2x1 plus 2x2. Okay, is this sum in W? How do we know? Well, we need to see whether the second coordinate is twice the first, and it is, right? So here it is. I guess you can easily see that if I factor the 2 out from here. Right, there it is. So the second coordinate is twice the first coordinate. So the first axiom is satisfied. Now let's take a look at the second one, second axiom. It's the commutative property. Well, that's also clear if you add the first. So let me write that here. Okay, that's the sum. And well, let's see if we commute the sum. Do we get the same thing? Yeah, you will see that obviously we do get the same thing. But just write it down, and that will show it. Okay, here it is. And obviously, these are real numbers, so we know how to deal with real numbers. x1 plus x2 is the same as x2 plus x1. And same thing here. This is the same as this. So the sum is commutative. Let's go to the third axiom. It's the associative property. So that also is quite straightforward. Just write it down. Okay, here's I need to pick 3 vectors this time, right, to do the associative property. So here's the first vector, here's the second vector, and the third vector. So the associative property says that it doesn't matter which way you add them, you're going to get the same thing. Well, that's what we want to show, right? So I pick the 3 vectors, I'm adding the last 2, and then let's see if it's the same as adding the first 2 first, right? So x1, 2x1, x2, 2x2, x3, 2x3. Okay, I'll let you do the work here. So if you expand this thing, obviously you're going to get x1 plus x2 plus x3, right? 2x1 plus 2x2 plus 2x3, which is the same. Okay? So there is the associative property. Now let's take a look at number 4. The vector space has a zero vector. Okay, we don't know who the zero vector is. Okay, don't assume right away that it's 0, 0. Okay, in this case it will be 0, 0, but don't assume that. Okay, so first let's find out who the zero vector is. So the zero vector is a guy such that if I add one vector in the vector space, okay, here's a vector in the vector space. If I add the zero vector, I should get the same original vector back. Okay? Okay, who is that zero vector? Well, just set up a little equation here. So the zero vector, because it's in W, it has to obey the same structure, okay? The zero vector is in W, then it has to obey this form here, right? The second coordinate is twice the first coordinate. Well, let's see if I put A here, and then the second coordinate has to be 2A, right? We can find out that that A is actually 0, but we don't know at this point. So, and then just solve this thing. This would be x1 plus A, and then 2x1 plus 2A equals to x1, 2x1. Then you can see if you look at the first coordinate, this has to be equal to this. Therefore, A has to be equal to 0. Okay, let's look at the second coordinate and see if it's okay. Yeah, if I cancel 2x1 with 2x1, so 2A is 0, so A is 0. So it looks like 0 vector is 0, 0. Okay, we found it, and as you can see, if I add it to any vector in W, I get the vector back. Let's look at property number 5. Here it is. Property number 5 is the additive inverse. So for every vector in W, we need to come up with a special vector that when you add to the original vector, you get the 0 vector. So here's a general vector, and let's find out who the additive inverse is. Okay, I don't know who it is, so let's put A and 2A. Okay, if I add this to this, I need to get the 0 vector. Okay, so this will be the additive inverse of x1 to x1. Okay, just solve the equation now. This would give you x1 plus A, 2x1 plus 2A equals to the 0 vector. And this time I put 0, 0 because I know now that the 0 vector is actually 0, 0. Okay, so that means you can't do property 5. You can't prove property 5 before you prove property 4. Okay, so here, if you make this coordinate equal to this coordinate, it turns out that A would be negative x1. And let's see what happens. Let's see if it's okay for the second coordinate, okay? This would be 2A equals to negative 2x1, and divide by 2 on both sides, A equals to negative x1. So it's okay, it's possible to find, and so the additive inverse of x1 to x1 is negative x1 minus 2x1. Okay, let's go ahead and prove property number 6. That's the closure of the scalar multiplication. Okay, well, I'll pick a scalar, multiply by a vector in W. Okay, is this still in W? Well, let's find out. This would be CX1. This would be 2CX1. How do we know that this is in W? Well, is the second coordinate twice the first coordinate? Yes. So this is in W. Property number 7. That's the distributive property. Pick two scalars now. Well, actually two vectors and one scalar. Property number 8 will be two scalars with one vector. So here is a scalar and two vectors. x1, 2x1 plus x2, 2x2. Okay. And just multiply this out. Right, this would be c. Well, first add inside. This would give you x1 plus x2. And then, let me write this down for you. Okay. That is the first part, and then I need to show that this is equal to c times the first vector plus c times the second vector, and that's very easy. Just expand that out. So c times the first vector plus c times the second vector, and if you expand this out, right, you're going to see the same thing. Right, so this is equal to that. So property number 7 is satisfied. Number 8, you do the same thing, but now with two scalars, okay, c plus d. So expand that part. And then see, I need to show that this is the same as c x1, 2x1 plus dx1, 2x1. Okay. And okay, let's expand this out. Here it is. Now we add and combine the scalars. So this would be cx1 plus dx1, and then the second coordinates, 2cx1 plus 2dx1. Right. So at this point you can see it's the same as this one here. You can collect the x1s here, factor x1 to get the c plus dx1, and then you can collect the c in the 2x1 to get the c plus d there. Okay, that's property number 8. Property number 9 is the associative property for those scalars. So pretty easy. Let me write that down here. So I need to show that this is equal to this, so just expand that out. This will be c dx1 to dx1, and then I'll multiply the c dx1 to c dx1. And then here, that's pretty easy here. C dx1, and then to c dx1. They're equal. Finally, the last property is to show that if you multiply the scalar 1 times the vector, you get the vector back. You need to show that that is satisfied. It seems so obvious, but you know, that's one of the properties that we need to show. So if I multiply 1 times the vector, now the vector is, a vector in W is always of this form, x1, 2x1. Now, let's see what happens, and then I need to show that that is really the vector back, right? And x1, 2x1. So this would be 1 times x1, 2 times 1 times x1, and that's obviously x1, 2x1. Okay, so there it is. So that's the end of the exercise. So W is a vector space. Okay.